sort of the homogeneous aspects of inflation, which we just touched on at the beginning at the end of the last lecture. And then there are a couple important calculations here that I'm going to leave. I'll just sketch on the board, but primarily leave to work out in the tutorial this afternoon. And then we're going to introduce QFT and curved spacetime. Get some of the most important concepts, and then tomorrow, so this is today, and then tomorrow we will do sort of the initial simplest application, which is to the Unruh effect, which is this famous fact that an accelerated observer sees what, according to an inertial observer, would be the vacuum, the accelerated observer sees as a thermal distribution of particles. And that ultimately is really essentially identical to the phenomenon of black hole radiation. It's just an easier way to get to it. So we'll go through that calculation tomorrow and understand. And then the idea is to see. In Ruth's course, did she do the Unruh effect? No. Okay. Yeah, that's a very good thing. And anyway, so we'll want to understand the relationship between this whole business about, you may have heard, like thermal states are periodic and imaginary time and so on, and there's entropy associated with horizons, all this business. Just to say that probably not tomorrow, but probably the day after, we will then get a chance to apply that to inflation and see how it all relates to the proposed mechanism for the generation of the primordial fluctuations in the early universe. I should also say today's lecture notes on QFT and curved spacetime, well, today and tomorrow's, they're not done yet, so I haven't posted them to the wiki yet, but they'll be available tomorrow. So never fear. OK, so inflation. So again, what I want to stress is that the key idea is supposed to be that if I plot things in co-moving coordinates, co-moving spatial coordinates, then again, there are two. Just like I can take any co-moving distance. In other words, the distance according to the fixed grid of spatial coordinates that are marked on my sphere with markers, and just sit there on the sphere as the universe expands. If I want to convert any co-moving distance, that is the coordinate distance between those coordinates, into a physical distance, the actual number of rulers that I would have to lay down if I froze the universe at that moment in time and laid down meter sticks until I got from one place to the other, the physical distance is related to the co-moving distance by the scale factor at that time. And so yesterday we said that, in particular, there's an important distance characterizing the universe at any given time, which is the Hubble distance, the Hubble radius. So RH at time t is 1 over the Hubble expansion rate at that time. Or really, it's c times that, but I work in units where c is equal to 1. So this is a physical distance. I can convert it to a co-moving distance so the co-moving Hubble radius, let's call that r hat. Just like with any physical distance, I divide by a to get the corresponding co-moving quantity. So the co-moving Hubble radius, the Hubble radius expressed in co-moving coordinates, is 1 over ah. And again, we said physically we can interpret this as the ratio of the Hubble radius, 1 over ah, to the radius of curvature of the 3 surface, if the 3 surface I live on is a curved one. So the idea is that, well, there's a simple observation, which is that ah here is, well, h is just a dot over a. So this is a times a dot over a. In other words, it's just a dot. Okay? So if the universe is decelerating, if a double dot is less than 0, that's precisely saying that a dot is decreasing. And but then since a dot is ah, that 1 over ah is increasing. So the co-moving Hubble radius is increasing as the universe decelerates. And conversely, when the universe accelerates, that's exactly saying that a dot is increasing, the expansion rate is increasing, and that is saying that the co-moving Hubble distance is shrinking. Okay, so here is U at the center of, at the origin of co-moving coordinates. Okay, these are your co-moving spatial coordinates on the board. So if I draw, now you were not born yet at the beginning of the radiation-dominated era, but had you been, and you drew the co-moving Hubble sphere around you at that time, you drew a little sphere with radius 1 over ah at that time, it would be some tiny little sphere. And then since the universe has been decelerating ever since then, it's been dominated by radiation, relativistic particles, or non-relativistic massive particles. And you saw earlier in the first week of the class that those give rise, that when you solve the Friedmann equation, those give rise to a decelerated evolution. So ever since the beginning of radiation domination, the universe has been decelerating. And so according to this, the Hubble sphere, co-moving Hubble sphere, has been increasing in size. And so today, it's some gigantic sphere, many orders of magnitude larger than it was at the beginning of radiation domination. And if the universe had been radiation dominated all the way back to the Big Bang, so we went back to the Big Bang and this sphere just got smaller and smaller and smaller until it shrunk to 0 size around you. Okay, then there are a bunch of puzzles which we're about to describe. That gives rise to a bunch of puzzles, and inflation's solution to those puzzles is just to say, that's not what happened. This sphere, you can't think of it as just shrinking and shrinking all the way back to the Big Bang. It shrank and shrank and shrank back to the beginning of the radiation-dominated epoch. But then prior to that, there was a period where the universe was accelerating, and during that period, the sphere had the opposite behavior. So in other words, at early times, the sphere was actually huge. And then during the accelerated period, which is called inflation, the hypothetical accelerated period, which is called inflation, prior to radiation domination, the sphere shrunk down to this tiny guy, and then the ordinary radiation-dominated era began, and the sphere basically bounced and expanded out to its current size. And again, the simple geometric statement is that the following 3 puzzles are all alleviated if the initial size of the sphere, the initial size of the co-moving Hubble sphere around you, if the initial guy is bigger than today, bigger than the sphere today. If the initial shrinking was more than the subsequent expansion. Okay, so now let's see why that is that's if you want the image to freeze in your mind. But let's just see that applied to 3 different puzzles: the so-called flatness puzzle, the horizon puzzle, and the monopole puzzle. And then also, the other thing we want to say is, at the same time as we're seeing how inflation alleviates these things, we also want to consider, how convinced we ought to be by inflation's explanation of these things. Is it really, is it time yet to give up looking for alternative or better explanations for these phenomena? And that's something we want to again consider when we get to perturbations. Basically, because on the one hand, I want to express to you why the majority of the community now thinks that inflation probably did take place in the early universe. It's become sort of a consensus opinion. And, but also I hope to, I more or less think it's solidified in excess of the evidence, and that opinion has it, that people are sort of, there's a sociological effect where everyone is convincing one another, and everyone is taking their first cosmology course and being taught that inflation is right. Yeah.
So with this picture, how special is today? So like, if some societies of tomorrow were to measure the universe and come up with the same puzzles, but for some reason their co-moving Hubble radius is larger than it was in the initial conditions, like, do you have to keep on pushing these initial conditions to infinity, or is there a prediction with what's like the maximal initial conditions you need?
Yeah, well, so that actually is exactly a thing you're going to work out in the tutorial this afternoon. But to make a long story short, you can't really. The thing you will calculate in the tutorial this afternoon is how much does the universe have to shrink during inflation in order to outstrip the subsequent expansion that took place during the remainder of the universe. That you can calculate. Now, how much did it actually shrink? And so how far into the future will this explanation continue to explain analogous observations if they continue to be made into the future? We can't answer that because we don't know what the correct microphysical model of inflation was. We don't have a theory of initial conditions, and we don't know exactly what model drove inflation. If you knew those things, you could predict how much the universe actually expanded, and so you could predict how far into the future would you suddenly begin to see that the universe wasn't flat, begin to see that the universe, begin to see the finiteness of the horizon. But we don't know that at the moment. Okay, so what is the flatness puzzle? The flatness puzzle deserves its own board. Okay, so you remember from the first week that there are basically two key equations that describe the evolution of the FRW universe. One is the Friedmann equation, 8 pi g over 3 rho minus k over a squared. And the other is the continuity equation. To discuss the flatness puzzle, it's useful to just manipulate these two equations into two equivalent equations that are sort of a little bit more immediately relevant to the question, that just make things more transparent. So to do that, let's one of the equations was I just want to divide by h squared on both sides here. So equation number 1, I get 1 on the left-hand side, and then if I divide by h squared in this term, I get 8 pi g over 3 h squared. That's really 1 over the critical density. Remember, the critical density is 3h squared divided by 8 pi g. So this is rho over rho critical. And then minus k over a squared becomes minus k over ah all squared. So in other words, so this is this quantity. This is k times the co-moving Hubble radius squared, this quantity we've just been talking about. Okay, so that's the first equation. Then the second guy, so let's differentiate this guy with respect to time, and then use this guy to simplify it. So if we differentiate this with respect to time, it becomes 2h h dot on this side. This side becomes 8 pi g over 3 rho dot. And then, so this becomes plus 2 k a dot over a cubed, right, if I differentiate it. Now I'll take a dot over one of those a's and call it h. So that, in other words, this becomes 2k h over a squared, if I haven't made an algebra mistake. And then let me use the continuity equation to remove this rho dot. Okay. So this will be 8 pi g over 3 times minus 3h rho plus p, and then plus 2k h over a squared. So now I can divide an overall h out of this side and this side. Okay, so I'll kill this h, and over here I'll kill an h in each term. So now this becomes 2h dot Well, 2h dot is really, so h is a dot over a. So h dot is a double dot over a. That's one term from differentiating the numerator of h. And then minus a dot squared over a squared from differentiating the denominator. But this is just h squared, so I'll use the Hubble equation. I'll use the Friedmann equation to remove that guy. So I have 2 a double dot over a minus 2h squared. Using that, that's minus 2 times 8 pi g over 3 rho minus k over a squared. And that, OK, the algebra is almost over. And that is now equal to this thing with the h's removed. So this is minus 8 pi g rho plus p plus 2k over a squared. OK, so this 2k over a squared cancels against this 2k over a squared. And then if I just pull this row to the right-hand side and simplify, I get, so I just isolate the a double dot term on the left-hand side. I get that it's equal to minus 4 pi g over 3 rho plus 3p. OK, so these are the two equations I want to look at. As I say, they're completely equivalent to these two equations. You can go back and forth between them. So let's first look at what this guy is saying. So this guy is saying that this equation tells us when a double dot, when the acceleration of the universe will be positive or negative. So we have a key minus sign here. So rho is positive. The energy density is, for sensible matter, is positive. So if we neglected this term, this equation would say that a double dot is negative because it's minus a positive number. But pressure need not be positive. And as we'll see, for simple systems, including a cosmological constant or a scalar field that can be sufficiently negative to cancel out this guy. And so the dominant thing here could be a negative thing times a negative thing, and we could get a positive acceleration. So if the pressure is sufficiently negative, that's when we get acceleration. In particular, acceleration we see from this equation is equivalent to the W, the ratio of the pressure to the energy density, being less than minus 1/3. OK, that's the condition for acceleration. And again, if we accelerate that's the situation in which the Hubble radius is the co-moving Hubble radius is shrinking rather than expanding. OK, so now let's turn to this equation. What is this guy saying? Well, so as this thing grows, so again, this is a constant times the co-moving Hubble radius squared. So during a decelerating phase, like our ordinary matter or radiation dominated epochs, this term is growing and growing and growing. So let's see. Maybe let me say it backwards. An observed fact is that today, rho is observed to be equal to rho critical plus or minus 1%. Okay, that's the current observational status. So this makes up a tiny contribution at the present time. But in the decelerating phase, if we look backwards in time, the co-moving radius was shrinking. So this made up an even tinier contribution as we look backward through the history of the universe. So even today, this term is tiny. And if we asked at any earlier time, we would find it was even more tiny. So today it's 0 to within a part in 10 to the 2. But back at the time of Big Bang nucleosynthesis, for example, that implies that this thing was 0 to within a part in 10 to the minus 31. Part in 10 to the 31. So the question is why? And it's stated in the forward direction, what made this thing so tiny at early times that even though it's been expanding and expanding by many orders of magnitude since the beginning of the radiation-dominated epoch, it still makes up a negligible contribution to the right-hand side of this equation. OK, and so in geometrical terms, that's saying, so again, if we draw the universe as a 3-sphere, the fact that this is so tiny that we haven't been able to observe whether it is non-zero yet is exactly saying that if this is us, this is the 3-sphere we live on, and we draw the radius of our co-moving Hubble sphere around us, that at the present time, the radius of our co-moving Hubble sphere, even though it's been expanding and expanding and expanding since the beginning of the radiation-dominated epoch, the radius of our current Hubble sphere is so small relative to the radius of the 3-sphere that we might live on, or relative to the curvature radius of the surface that we live on, that we haven't been able to detect that curvature radius yet. As far as all our observations can tell us, they're fit by saying that we live on a little flat plane tangent to the surface here. And so again, the question is why? And inflation's explanation to this is that, well, maybe at some early time, this Hubble sphere was not a particularly tiny fraction of the radius of the sphere as a whole. You know, maybe initially it was some order 1 fraction of the radius of the sphere. That might be in some sense, the natural explanation. But then if there was a exponentially long period of accelerated expansion, if there was an exponential amount of accelerated expansion, this sphere would be shrunk to an exponentially small sphere. And so if it had been shrunk to a sufficiently small sphere by the beginning of the radiation-dominated epoch, by the beginning of the decelerated expansion, then we won't be surprised to find that it hasn't had a chance to grow back to a large fraction of the 3-sphere by the present day. Okay, so that's the solution proposed by inflation to the flatness problem. The horizon problem and monopole problems, there we can both be pretty brief about both of those. So the horizon problem, we really already met this at the beginning of the course. I already mentioned this fact that we said that around an observer in an FRW background, there's a future horizon. In general, unlike in a static black hole spacetime where there is, a horizon around the black hole. In cosmology, there is this distinction between a future horizon and a past horizon. So if you're an observer at a given time, your future horizon is you may have a future horizon, that is to say, some surface beyond which you're never going to be able to communicate. You're never going to be able to send a signal to other observers on the 3-sphere. Okay, there may be some surface beyond which the light signal you send now will simply never, by the end of the universe, reach people out here. And then your past horizon is, if you're here, there's some finite patch of the sphere from which you have been able to receive signals since the beginning of the universe. And a signal over here that was emitted even at the very beginning of the universe just hasn't had a chance to reach you yet. So that's your past horizon. And we saw that, in particular, if you have a universe that decelerates forever, people have a past horizon around them. So this is the situation in an ordinary decelerating universe. On the other hand, if you have a universe that's always accelerating, those folks have a future horizon around them, and the way we saw it was, just to remind you, we went to coordinates. The easiest way to see it was to go to coordinates in which you pulled out an overall factor of a squared in front of the metric. So in other words, you went to coordinates with where the time coordinate was the so-called conformal time instead of the proper time t. And also sort of conformal radial coordinate. And there's the angular part of the metric that we didn't need to worry about. Again, we said, the way we figured this out is we integrated the equation for a past-going null geodesic. So a null geodesic that satisfied d eta is equal to minus d chi throughout its trip to u at the origin. The point basically is that, so remember d eta is equal to dt over a. That's the coordinate transformation we had to do to pull out the a in front of the whole metric, if you remember. So now one way to see sort of easily without solving things that this statement is true is that if you just change integration variables to a here. So in other words, let me multiply and divide by dA. So the dA in the numerator will become my new differential. The dA in the denominator I'll combine with this dt to make an a dot. So in other words, this will become 1 over a dot dA over a. And then this is our old friend AH. So this is really the co-moving Hubble radius times dA over a. So if the co-moving Hubble radius were constant, so now we're integrating this from 0, from when the scale factor was 0, the Big Bang, up until the present time. If the co-moving Hubble radius was constant, this would integrate to log a, and it would diverge. It would just barely diverge. It would diverge logarithmically at the lower boundary here, right? Log of 0 is infinity. But if this guy now goes as any positive, if this guy now goes to 0 at the origin, as a goes to 0, if the co-moving Hubble radius shrinks to 0 as any positive power of a, that'll be enough to make this integral converge. So that's the statement that if the co-moving Hubble radius is growing as a positive power of a, that's saying that the universe is decelerating. And alternatively, if this guy diverges as any arbitrarily small but negative power as a goes to 0, that'll be enough to make this integral diverge. Confirm the logarithmic divergence of this guy. So that's just a way to see here that indeed acceleration removes the past horizon. The reason that's important, well, I personally am not 100% clear how important that is, but the point is that if you look at your map of the cosmic microwave background, it has the same temperature at every point on the sky. It has a thermal spectrum at every point on the sky with almost exactly the same temperature. So it looks a lot like a system that has managed to come into equilibrium with itself. Yeah?
If we assume that the universe had homogeneous initial conditions and that the same laws of physics apply everywhere, why should we be worried about the fact that it's similar?
Yes, I totally agree with you. So in other words, let's first say the ordinary perspective that people present, and then we'll give the Kieran alternative. Okay, so the ordinary perspective is, wow, I point my telescope up, everywhere I look, I get a perfect black body spectrum suggesting a gas in thermal equilibrium. Furthermore, in every direction I look on the sky, the temperature is exactly the same. It looks like every direction on the sky not only came into equilibrium locally, but came into equilibrium with every other direction on the sky. So it looks like somehow the whole region of the universe that we're able to observe back at that epoch, a few 100,000 years after the Big Bang, somehow our whole observable patch of the universe had apparently come into equilibrium with itself. But then if you actually trace back, around this point, how big was its past horizon if the universe had been always decelerating? It's too small to have let it make contact at all, let alone come into equilibrium with this point over here. So these 2 points on the sky, both if the universe had been decelerating ever since the Big Bang until this moment, then this guy would be surrounded by a past horizon that big, and this guy would too. And so, how did they ever manage to come into causal contact? Now, I personally do not find this to be a very convincing argument, because I kind of share Kieran's feeling that, the bottom line is that we don't have a theory of initial conditions for the universe. Or in fact, we do. We do have a proposed theory of initial conditions for the early universe. And that theory, well, in general, it wouldn't be surprising if you had some theory for the initial conditions of the universe, and it predicted as the most probable state, or the most preferred state, the lowest cost state in some sense, if the universe is given birth to by some spontaneous process, but different shapes of the universe have a different cost. It wouldn't be surprising if the most lowest cost state had the fewest ripples in it and was perfectly homogeneous. And that we'll see, hopefully, in the last lecture that is actually an explicit prediction of the Hartle-Hawking proposal, which, for my money, is the most beautiful proposal that's been found so far for the initial conditions of the universe. But so, yeah, I share the view that that's kind of only so-so evidence. But anyway, that definitely historically has made a big impression on people. Then the final one, you're about to cut me off in 2 minutes. I'm really under the gun here, but this is good. OK, so finally, there's the monopole problem. So here, in brief, so John Preskill, current member of PI's Scientific Advisory Committee, when he was a grad student in the late 70s, realized that, OK, so in the 70s, grand unified theories, the first grand unified theories had just been discovered. And there were reasons that I won't go into now that people were so enamored of them, they thought they just had to be right. And so John Preskill noticed that, well, if really the universe is described by one of these grand unified theories, then as the universe cooled through the grand unified temperature, if it had been decelerating ever since the Big Bang, if it had just been ordinary radiation-dominated evolution, then, OK, then as you cool through the gut scale, as you cool through the characteristic energy scale of those theories, spontaneous symmetry breaking happens. The grand unified symmetry breaks down to the symmetry of the standard model. But again, you expect that spontaneous symmetry breaking to occur spontaneously in some direction or other. The Higgs falls down its potential in some direction or other. But in two regions that haven't had a chance to exchange light signals, the Higgs can't coordinate to coherently fall in one direction or another. You end up getting the field disordered on scale. The bosonic fields are disordered on scales larger than the horizon size at that time. And as a result, you end up predicting that these stable defects, these stable field configurations that get formed called magnetic monopoles, each of which is then stable, lives for the rest of the universe. So each of them has a big mass by normal particle physics standards. So a proton weighs 1 GeV. These things would each weigh 10 to the 16 GeV. And you would have about 1 per Hubble volume at that time. So the Hubble volume at that time is that little tiny sphere that I drew up there on that tiny co-moving Hubble sphere. And so within today's big sphere, if you break it up into a lot of tiny little spheres of that tiny size, I need to bring down the board. So we take our big co-moving Hubble sphere today, break it up into tiny little pixels with size given by the tiny sphere at the beginning of radiation domination, put, roughly speaking, one monopole in each of those, and then ask how much mass is there in monopoles today, and it's stupendously larger than the critical density today. So it's completely in conflict with observations. OK, so inflation's proposed explanation for that is that grand unification, if grand unification is correct, the symmetry breaking took place before inflation. So then you predict that one of these magnetic monopoles should form per that big sphere that I've labeled initial, the initial gigantic sphere. So in other words, suddenly, instead of predicting many, many, many monopoles inside the sphere labeled today, you predict less than one monopole inside the sphere labeled today, because you predict one monopole inside the sphere labeled initial up there. OK, so in short, that is inflation's proposed solution to that problem. Yeah, again, that made a very big impression on people at the time, because at the time, people were very sure that grand unification was kind of going to be on the right track. Since then, two things have happened. One is that grand unification was supposed to predict proton decay, and we haven't seen that. And the other thing is that at the time, experiments looked like if you took the data at the time and used the renormalization group to extrapolate the three gauge couplings up to high energies, they all seem to cross right at a point in agreement with the predictions of grand unification. Today we know that they don't cross anymore. So they don't cross. They come close, but they don't cross. Supersymmetry is supposed to solve both those problems. If you add low energy supersymmetry, it can fix both those problems. It makes the three guys cross again, and it moves the energy scale up high enough that we don't have to get too upset about not seeing proton decay yet. So anyway, so you can work around it. On the other hand, we haven't seen now evidence at the LHC for low energy supersymmetry. But again, it's not definitive. Anyway, suffice it to say, it's a little bit up in the air. Certainly, the case for grand unification has not gotten stronger since the 70s from an observational standpoint. And yeah, arguably I would say has gotten weaker, although certainly by no means is ruled out. Yeah.
So does this observation, I guess, require that the universe did not start out in some highly entangled state?
So again, yeah, that's another good point. So just like Kieran's observation about the previous problem, the horizon problem, that if you had a theory of initial conditions that predicted something that was very far from random for the initial state, your thinking would be very changed about that. Similarly here, the idea here is that the field is in some sense born random and uncorrelated in different patches of the universe, so that that's where this estimate comes from, that you get one magnetic monopole per Hubble volume at that time. And again, yeah, it's basically that's maybe a natural estimate in the absence of a theory of initial conditions, but the same objection applies, that if the initial conditions naturally gave rise to a highly correlated initial state for the field, you might have to rethink whether the estimate of the number of monopoles is correct. That's another thing. Yeah. OK. Yeah. So I should. So that's. Maybe I'll just say. Well, let me pause for a joke. So today I have a topological joke. So I ask you to all do it with me. OK. So just cross your hands here. In fact, you might just want to stand up to give yourself room to really do this. OK. Everybody on their feet. Come on. You too, David. OK. Now like this. OK. Now take your index fingers put them on your nose. Squeeze your nose. Make sure your index fingers are crossed. OK. Everybody got it? And now just release them. No?
Yeah.
You guys, who should we try this again? Do you guys all have the same number of fingers on both hands? One more time. Yeah, I like everybody's. This is a great feeling of power. Now just release. See, Kieran's still stuck. Kieran, you may have just discovered that your fingers don't have the same number of fingers on both hands. Anyway, there is a. I leave it to you. Some people had it work. Some people didn't. What is going on? What is wrong with those people whose hands did not, who were not able to disentangle their hands? Some of you did, to my great disappointment. I was hoping everybody was going to have their hands stuck and not be able to do it, but unfortunately, about half of the class did. Did exactly what I said. Anyway, I leave it to you. I don't know if you would call that a joke or not. It was very entertaining for me. I liked talking about it. I liked speculating that Kieran had a different number of fingers on each hand. But for me, that's a joke. So my threshold for what is a joke is really pretty low. OK. So I just want to say one more thing about inflation. OK, now you're really on the ball. So I've already gone 5 minutes past where I'm supposed to. If I spend more than 5 minutes saying the following thing, call me.
Are you pressing snooze?
I guess I am pressing snooze. Yes. I just have one more thing I want to say about just to introduce what you will do in the tutorial this afternoon. So that is the following. So it's all well and good to say abstractly that the universe should accelerate at early times and then start decelerating at late times. Are there plausible physical models that do that? So the answer is yes. That there's quite a simple model that does it. If I just take the action for Einstein gravity, and then I just add to it the simplest matter content I can think of. A single scalar field with potential v of phi. OK, in fact, let me take the simplest potential I can think of. I'll just take the potential for a free scalar field, 1/2 m squared phi squared. OK, so this guy will do the trick, and so this is so in particular what does it do? Well, if you so as you'll work out so you can vary this action with respect to phi and find that the equation of motion for phi is the Klein-Gordon equation, where this guy, Box, is the wave operator in curved space. And if you just plug in the FRW metric here and take phi to be a homogeneous field, so if you focus on field configurations phi that don't depend on space, just depend on time, and you take the metric to be the FRW metric and expand out that wave operator, you find that the equation of motion for phi is like this. OK, and so what happens here? Well, this is so if we didn't have this term, phi double dot plus m squared phi is equal to 0. That's the equation for a harmonic oscillator with frequency m. This term is nothing but, you know, if phi double dot is the acceleration of phi and m squared phi is the restoring force of a spring, you know, if we think of this as an ordinary harmonic oscillator and we think of this as x double dot plus k, x is equal to 0, the equation of motion for a particle on a spring in classical mechanics, this guy, some positive coefficient times x dot, in other words, times the velocity, that is just an ordinary friction force. You learned in undergraduate classical mechanics that if you have this equation for a harmonic oscillator that's damped by a frictional force, there's two important regimes. If gamma is bigger than omega, then it's overdamped. The frictional force, it's overdamped, and so if I displace the spring of an overdamped system, if I displace the spring away from, so this is displacement of the spring from its equilibrium position, and this is time. For an overdamped system, it doesn't oscillate; it just gradually oozes back to the equilibrium position. On the other hand, if gamma is less than omega, it's underdamped. And the spring, in that case, oscillates, but with a gradually decaying amplitude. Okay, so now in cosmology, this equation is exactly the same. The only difference is that instead of a constant gamma, like you solved in freshman classical mechanics, h is time-dependent, and in particular, as the universe expands, h is going to be decreasing. And so, in fact, in this problem, h will be just given by the Friedmann equation, where rho is nothing but the rho coming from the scalar field. So rho, it turns out, for a scalar field, is its kinetic energy plus its potential energy, as you might expect. Okay, so now h will be dropping as the universe expands. And so in this case, what will happen is at early times when h is big enough, we'll be in this overdamped regime. And the field will just be gradually oozing down its potential. So that's the regime in which this equation behaves like if you jump out of an airplane, you hit your terminal velocity. You accelerate until you reach a point where the force of gravity pulling you down is equal to the frictional force pushing you up. So the velocity with which you ooze down the potential so initially, in other words, you start the field up here. Initially, when h is sufficiently big, it just oozes down at a rate given by balancing these two terms against each other. But then, eventually, as it's oozing down, h is decreasing. Eventually, h gets low enough that you get into this underdamped regime, at which point this term becomes not so important. And in fact, you can do a nice change of variables to remove it. So if you change variables from phi to a to the minus 3/2 chi, let's say, just redefine a new field variable, chi, where I've just pulled out a factor of a to the minus 3/2. That minus 3/2 is, that exponent there is chosen exactly because this is a 3. It turns out if you plug in this transformation, the new equation of motion for chi has no single derivative term. It just looks like m squared plus a little correction. So it just looks like a harmonic oscillator, but now with an almost constant mass, a little correction that you can work out, but that is negligible in this regime where this guy is smaller than this guy. So now, in other words, what happens is that, roughly speaking, the field phi behaves like a to the minus 3/2 cosine mt. So now it oscillates back and forth in its potential with frequency m, but with an amplitude that's gradually decaying away as a to the minus 3/2 as the universe expands. So if you now check the expression for rho for a scalar field, its energy density is given by this. The expression for p, as again you'll check, is given by the same thing with a minus sign. So if you compare p to rho in the initial overdamped phase, you'll find that p over rho is less than minus 1/3. In fact, it's about equal to minus 1. That equation is not true, but p over rho you'll find is about equal to minus 1, which in particular is less than minus 1/3. Yeah, sorry, I just need one more 1 minute snooze. So in other words, the universe is accelerating. Initially, the universe is accelerating in this potential. But then once you cross over into this regime, suddenly P over rho, you'll find, is approximately equal to 0, which is greater than -1/3, so the universe is decelerating. So this is a very simple model that shows that the universe can indeed have a natural matter content that transitions from acceleration to deceleration. And the amazing thing is that then when we just neglected quantum mechanics and we neglected the perturbations in phi. But now if you put the perturbations in phi in their ground state and just ask how they're excited by the motion of the field and the acceleration of the universe during this phase, you find that the fluctuations are quantum mechanically turned into a scale invariant spectrum that matches the primordial spectrum that we appear to observe in the early universe. So that's the thing we want to get to next. But the things which you'll check in the tutorial this afternoon have to do with these homogeneous arguments and this homogeneous behavior of the scalar field that I just described. Okay, so now I'm ready to go on to quantum field theory and curved spacetime. Are there any questions about that? You guys want another calisthenic exercise where we all get up and... Because I don't have another one. So if you did, I'm glad no one said yes, because then it would be humiliating for me. OK, so quantum field theory and curved spacetime. Well, so maybe with 10 minutes here, I really just want to get across the most essential concept, and then we'll do things properly and do the Unruh effect tomorrow. But so again, let's just focus on the simplest. Let's first do QFT in flat space. And for the simplest theory we can think of, again, a single scalar field. Again, a free scalar field. So completely quadratic Lagrangian. A single scalar field of mass m. So again, the equation of motion for this, we vary S and find the equation of motion. And it's the Klein-Gordon equation in flat space, where eta mu nu here is the Minkowski metric, and this is the flat space wave operator. OK. So now, jumping a little bit, remember that when you quantize this system, what you do, well, so Dirac taught us how to take any action and quantize it. We take the degrees of freedom, we calculate the momentum conjugate to the degree of freedom, which in this case is phi. So that's obtained by just taking the derivative of L with respect to the time derivative of that quantity. So the momentum conjugate to phi is dl d phi dot. So in this case, that's just phi dot. We quantize by promoting pi and phi to operators, space-time dependent operators satisfying the canonical commutation relations, which are that phi at x and t commutes with phi at any other position x prime and t. So those guys commute. Similarly, the pi's commute. But phi and its conjugate momentum do not commute. Okay. Okay, and again, this is just you know, this is the usual rule. If you have a Lagrangian that depends on q and q dot, the momentum p that's conjugate to q is defined by partial L d partial q, and then Dirac tells us to quantize by taking q commutes with q and p commutes with p, but Q and P do not commute. Their commutator is IH bar. Okay, so this is exactly the same as what we did over here. And then we say, okay, so that's all correct, but a more convenient language in which to discuss these fields is in terms of particles, and that we do that by going to Fourier space. So we say, okay, the solutions of this equation are positive frequency. They're positive frequency plane wave solutions. They're like e to the I k dot x minus omega t. That's a solution if omega is equal to the square root of k squared plus m squared. And then, so these solutions, okay, properly normalized. Let's. I haven't defined the norm yet, but anyway, to properly normalize them, you put a little appropriate constant in front. So these solutions, let's call them phi sub k, and they're complex conjugates, the corresponding negative frequency plane waves. Those guys together form a complete set of a complete orthonormal set of solutions for this equation. So we can take any solution and expand it in terms of them. So that expansion looks like some Fourier coefficients times the solutions. Where every time I have a term like this, the complex conjugate term is appearing because, again, I'm talking about a real scalar field, so I have to write down combinations that are real. And then when written out this way, the nice thing is that these commutation relations are now equivalent to commutation relations for the Fourier coefficients. So instead of so when we promoted the fields phi to operators, that was equivalent to promoting the Fourier coefficients A and A star to operators A and A dagger, which satisfy the familiar algebra of creation and annihilation operators that you meet from when you do the harmonic oscillator. Okay, so we find that those above commutation relations are equivalent to saying that the operators A and A dagger commute with the A's commute with the A's, and the A daggers commute with the A daggers, but the A's do not commute with the A daggers. And instead, okay, they don't commute with the A daggers. And so we're already familiar with what the representation theory of these guys look like from the harmonic oscillator. Just like in the harmonic oscillator, we have the ground state, which is the guy that's annihilated by. So in the harmonic oscillator, well, anyway, you remember the harmonic oscillator. In the harmonic oscillator, you had an original Lagrangian that was like 1/2 p squared minus 1/2 q squared, just like we have here. We have 1/2. We roughly speaking have 1/2 p squared minus 1/2 omega squared q squared. And you define creation and annihilation operators by q plus ip. And if you take the canonical commutation relations for these guys, for the q's and p's, if you take these commutation relations, that implies that the a's satisfy commutation relations we just, the sort of discrete versions of the continuous commutation relations we just found. And then you construct the state space, and well, the ground state is the state is the state that is annihilated by the annihilation operator, and then all the other eigenstates of the Hamiltonian are obtained by acting on the ground state with creation operators one or more times. Okay. If you want to create n excitations, you act on it n times. So here, this theory is just the same thing, but now there's a different creation and annihilation operator for each value of k. So the vacuum state is the guy that's annihilated by the annihilation operator for every value of k, and all the other eigenstates of the Hamiltonian are obtained by acting with the various creation operators for different k's on the vacuum state. And we interpret those as states with a certain number of particles in them. And if you want to measure how many particles are in a state, just like if you want to measure in the ordinary harmonic oscillator how many excitations you have, you use this number operator, n. You apply that to your state, and its eigenvalue tells you how many excitations are in that state. Similarly, if you want to find out how many excitations are in some state of the Hilbert space here, you apply the with wave number k, you apply the appropriate number operator for that wave number. Okay, which is constructed in exactly the analogous way. You probably can't see the board here because it's behind the podium, but okay. As I say, that was a little bit hasty, but it's all in the notes. Well, hopefully you've seen this before, but anyway, it's reviewed in the notes, which I haven't posted yet, but which will be posted soon. You know, now the essential point is that. So now, if we want to change, okay, I want that board back. So if we want to go to curve space now, what do? Well, we change the action to the corresponding curve space action. So we replace the flat metric by the curve space metric. We vary to get the equation of motion. It looks exactly the same way, except now this is the curve space wave operator. And the upshot is that, again, if we want to canonically quantize this system, we can again just do the same game where we expand the field like this. We expand the field as coefficients times positive and negative times a complete set of positive and negative frequency solutions of the wave equation. But now, these solutions, because we're in curved space, these solutions are no longer just simple plane waves like this. Okay, they don't just have this simple explicit form. You know, in an expanding cosmological background or in background of a black hole, they'll have some more complicated form than this. And now the essential point, the ultimate key point, is that in curved space, you in curved space, the point is that, so let's say I'm an observer over here, and I solve the wave equation over here. And according to me, I find the solutions locally to me in this little patch over here. Those solutions look like, you know, because locally, if I zoom in on a small enough patch around myself, it looks like I'm in Minkowski space. So if locally around me, the solutions look more or less like the Minkowski solutions. And in particular, there's a natural notion of what are the positive frequency solutions, the ones that oscillate like e to the minus I omega t near me, and versus the negative frequency solutions, the ones that oscillate like e to the plus I omega t near me. So in other words, there are the solutions where if I look at them in the complex plane above my point in space, you know, if I sit at my fixed point in space and look how they change in time, they go this direction in the complex plane. Those are the positive frequency solutions. And they're the negative frequency solutions that go this way. So anyway, I solve and I do my splitting, and I put my annihilation operators in front of the positive frequency solutions, and I put my creation operators in front of the negative frequency operators. Fine. So I think everything about my quantum field theory is perfectly sensible. But then, you know, the solutions to the wave equation don't just apply. You know, they're solutions over the whole manifold. So let me take those positive frequency solutions, let's say, and extend them. They extend into solutions over the whole manifold. And the problem is that now some other observer at some different point in the space-time goes through the same exercise, splits the field into positive and negative frequency solutions, puts his annihilation operators in front of his positive frequency solutions and his creation operators in front of his negative frequency solutions. But the point is that we don't agree about the split. Okay, so if you take my solutions and you extend them over to him, what I call the positive frequency solution, by the time it gets over here, he would call it some linear combination of a positive frequency and a negative frequency solution. And vice versa. If I take his positive frequency solutions and extend them back to me, I call his solutions a linear combination of positive and negative frequency. So another way to say that is that, according to him, what I called a creation operator is to him a linear combination of his creation and annihilation operators. And so what I called the vacuum state, the state that was annihilated by my annihilation operators, is different than what he calls the vacuum state, the state that is annihilated by all of his annihilation operators. And in particular, the state that I call the vacuum, which according to me has 0 particles in it, he thinks the exact same state is full of particles. And so the classic example of this is you don't even need to go, the thing we'll talk about tomorrow, you don't even need to go to curved space to see it. Just last minute here. Just in Minkowski space, there's the distinction between positive and negative frequency according to an observer who's inertial, who's moving with a constant velocity through Minkowski space. Alternatively, if you turn on a rocket and are an accelerating observer in Minkowski space, you, it turns out, have a different notion of what positive and negative frequency is according to your own proper time. So this person has one proper time according to which they decide what positive and negative frequency is. This guy has another proper time. And again, what looks like the vacuum state to the inertial observer will look like a thermal state, will look like a state with particles in it, with the number of particles set by the Boltzmann distribution. Anyway, so that's the and in the cosmological context, the idea is that as the universe expands, an observer living in the far past at the beginning of inflation, they would have one definition of what the vacuum was. And let's say that the universe started off in the vacuum according to their definition. Then subsequently, funny business happens. Now today, we have a different definition of what the vacuum is. And according to our definition of the vacuum, that initial definition, that initial state was full of particles. And those particles, we observe those particles as the observed primordial spectrum of fluctuations in the early universe, or in other words, the observed ripples in the cosmic microwave background. Okay, so that's the idea in short. I'll try to go through it more systematically tomorrow and do the Unruh effect. Because everyone lost interest in it, because it didn't have as dramatic an outcome. The thing here is that if it depends on whether you fold your hands like this or like this.